Good morning, everyone. This is Wentao. Today, I want to share a paper, Manipulating Black Box Networks for Centrality Promotion. This paper has been accepted by ICD 2021. As we all know, graphs or networks are everywhere, and examples can be social networks, web graphs, and so on. In a network, we are interested in answering the question like, what is the most important node? To answer these questions, different centralities have been proposed, and the basic one is degree. In the example graph, the degree of V9 is 4 because there are 4 neighbors of it. The degree of V10 is 1, so we say V9 is more important than V10 because its degree is larger. There are other centralities like closeness, betweenness, and so on. Although there are different definitions of centrality, but there is one thing common, that is, centralities can be used to identify important nodes. The important nodes, or the nodes with high centrality values, have superior positions over other nodes. Now, give you an example, that is, on a correlation network, the important nodes are likely to receive more citations. In view of this paper focused on the problem of manipulating the network, or just inserting edges or nodes in the network. And our purpose is like, for a target node, we want to promote it to become important. And our purpose is that if the node become important, they are likely to receive more citations. Due to the importance of this problem, there are many researches about it. And the common method is that for the target node, in our example is V4, it will select a node to establish an edge each time. So let's recall the graph before any insertion as the original graph. In the graph, we can compute the centrality value of V4, which is 1 over 23. Then we can know that the ranking of V4 is 9. Because on this original graph, we can see that there are 8 nodes with values higher than V4. Now, if we insert an edge in the graph, we obtain a new graph. And on this new graph, we can still compute the centrality value of V4, which is 1 over 21. As you see, the centrality values of the target node has been improved. Nevertheless, there are 2 limitations of this method. The first limitation is that this method assumes the network structure is null. Otherwise, the target node V4 do not know which node can be established on edge. However, for many third-party users, the network is actually a black box. So in this case, this method cannot work. Another limitation is that if we insert edges into the graph, other nodes can improve their values. Let me give you an example. Like if we insert the edge, the value of V2 has been improved from 1 over 22 to 1 over 20. And we see that in the new graph, the ranking of the target node stays the same. That means the promotion actually takes no effect. Therefore, we want to promote the ranking instead of the values, which can be more meaningful. To summarize, we have 2 goals in our paper. First, we need to ensure the network structure is unknown. The second goal is we want to promote the ranking instead of the score. However, the ranking promotion problem is quite a challenge, as we see that the problem of maximizing the ranking improvement amount is intractable. Moreover, it is even harder to approximate. What does that mean? It tells us we cannot guarantee the ranking improvement amount. The things get worse because now we assume the network is black box. So it's quite challenging now. In view of this, we just want to take a small step. Instead of guarantee the ranking improvement amount, we want to ask a question, can we improve the ranking of the target node by at least 1? Then we can update the second goal as promote ranking by 1. And now I will tell you how we can achieve these two goals. For the first goal, promotion on the black box networks actually is quite straightforward. If we do not know the original graph structure, what we can do is we can insert nodes and edges just around the target node. There are different ways to insert the edges, like we can insert multi-points. This strategy, we call it multi-point strategy. Moreover, we can create a click, then we call it the single click strategy. Finally, we can insert a double eyes, we call it the double eye strategy. Then in this way, we just insert new edges without the reference to the original graph. Then the black box network assumption is achieved. However, the second goal, to ensure the ranking will be definitely improved, is a quite non-trivial problem. Like, we want to give you an example to show the difficulty. For the eccentricity centrality, if we just pick an ambitious strategy, we can say that whether it will successful promote the ranking. Here we selected V3 as a tagging node, and we just insert some nodes randomly. After that, we find that the ranking of the tagging node stays the same. Here we just insert 4 nodes, and we can prove that if you insert 400, 4,000, and even 4 billion nodes in the graph, the ranking of the tagging node will not be improved. In our paper, we will show that instead of inserting multi-points, if you insert double line, the ranking of the tagging node will be improved for eccentricity. But why? Do you have any idea for this? So in our paper, our main contribution is to answer the question like, when will a strategy be effective for promotion? To answer this question, our idea is that for all the centralities, like degree, like closeness, we divided them into 2 groups. And the division and the condition for the division is that when we insert nodes into the graph, there are 2 cases for the nodes. The first case is that the values of all nodes can only be increased, and the centralities like betweenness and coldness can have this property. The second group of centralities like closeness, eccentricity have the properties like the values of all nodes can only be decreased if we insert nodes into the graph. Therefore, for the first type of centralities, if all nodes increase their centrality, we can select the strategy to ensure the target node have the maximum value gain. The logical is that when all the nodes increase their centrality values and the target node have the maximum increase, then at some moment, the target node can overtake other high value nodes and its ranking can be improved. We use a similar logical like if all nodes decrease their centrality values, and if we ensure that the target nodes have the minimum loss, then at some point its ranking will be improved because its centrality decrease is a minimum. So if we selected a strategy using this condition, we can ensure the strategy is effective for centrality. Now we will give you more detail about this idea. First, we want to show you the maximum gain principle. And we want to answer the question like, we need to prove that multi-point is effective for betweenness, even though the network is a black box network. And it needs to meet 3 conditions. As we see, if we just insert some nodes, for betweenness, the target node V4 has a rank from 4 to 2, which means its ranking has been improved from 6 to 1. So I will introduce the 3 conditions. The first condition is that the target node T has the maximum gain. As you see from this table, the increase of the target node V4 is 14.2. And we cannot find any other nodes whose increase is larger than the target node. This is the first condition. The second condition is that the value of the target node will overtake a higher value node V after inserting a certain amount of nodes. We still give you an example. Like in the original graph, the node V5 has a between its value 4, which is larger than the target node. But after we inserting larger than 3 nodes, in the new graph, the centrality value of the target nodes now is larger than the higher value node V5. In this way, the ranking of the target node will be improved by at least 1 because it overtakes a higher value node. But note that we insert additional nodes in the graph. There are some situations where the inserted nodes have a higher value. So the third condition is that we need to ensure the target node has a value no smaller than the inserted nodes. Still in this table, we find that the target node has a value which is larger than the insert nodes because the insert nodes all have centrality values, which is 0. And this is ensure the ranking not be overtaken by insert nodes. Then we can prove that if a strategy meets these 3 conditions for centrality, then it will be guaranteed to promote the ranking. And this answers the question why we can prove that the multi-point is effective for betweenness. In similar logical, we can prove that the single-click strategy is effective for coyness. Actually, you can design other strategies for other centrality if you meeting these 3 conditions. There are other cases that if all nodes can only decrease their centrality, we need to ensure the target node has the minimum loss. And using this logical, we can prove that the multi-point strategy is effective for closeness. Still, it has to meet 3 conditions. The first condition is that the target node T has a minimum loss. As we see from the table, that the target node has the minimum loss, and we cannot find other nodes whose loss is smaller than this. The second condition is similar to the maximum gain principle. That is, after we keep decreasing at a certain point, the value of the target node will overtake a higher value node. In our example, the node V7 has a value higher than the target node in the original graph. But after we inserting larger than 2.5 nodes, we can prove that in the new graph, the centrality value of the target node will overtake it. This, the third condition is that the target node T needs to have a value no smaller than the insert nodes. And we see that from the table, the target node have a centrality value larger than it. Using these 3 conditions, we can prove that the multi-point strategy is effective. Using the similar logical, we can prove that the double line is effective for eccentricity. So this closes the question why multi-point is not effective for eccentricity, but double line is effective because it meets the 3 conditions. Now we need to present our experiments. We use 2 real-world data sets, Wiki and Heap. As we see from the figure that in the updated graph, the ranking of the target nodes has been improved for the maximum gain principle. Similar, we find that for the minimum loss principle on the real-world graphs, the ranking has been improved by at least 1. Then we can draw the conclusion. In this paper, we focus on ranking promotion on black box networks, and we have 2 goals. For the first goal, we need to not to rely on the graph structure, and the second goal is that we design the principle-guided strategies, which provide 3 conditions. On the condition, the centrality value of the nodes will be proved. And that's all for the presentation. Thank you very much.
Yeah, thanks, Wentao. Yeah, the time is just Very well. Just finished in time. So let's open the audience, the question from the audience. You can use the chat box or raise hand, or even you just speak. Yeah, we provide first speak, first service.
I have a question.
Good, good, good. Yes, please go ahead.
Yeah, so in this ranking enhancement, so does it matters if some nodes other than the target nodes, their relative ranking like changes? Does it matter?
That's a good question. Actually, we do not care about whether their ranking will be improved or not. Our purpose is to ensure the ranking of the target node will be improved.
Okay, so only the target node, right?
Yeah.
Okay.
Any other question? Yeah, since we still have some minutes, can you explain your previous slide a little bit more detail about how to justify the advantage of the proposed method?
Okay.
Mm-hmm.
For the previous method, they can ensure the centrality value of the node be improved, but they cannot ensure the ranking of the target node be improved.
Mm-hmm.
This is the first limitation. And in our paper, we can ensure the ranking of the target node be improved. The second advantage is that the original methods are normally the gradient algorithm. Then they need to assume the network is a white box. They need to know the network structure. And in our method, we drop this requirement. We can assume the network is a black box. And these are the two advantages of our method.
Mm-hmm. Yeah, thank you.
Thank you.
Do we have a final question from our audience? Okay, then it's about time to finish this presentation. And thanks, Wentao, again. Yeah.
Thank you.